In this video, we're going to explore two new algorithms for building predictive models, and these two are random forest and gradient boosting. Random forest and gradient boosting are actually extensions of the decision tree algorithm, and we're going to discuss these in this video. We're going to give a theoretical overview. We're going to discuss what these are and why we want to do them. So let's start off by reviewing decision trees. Now, in previous lectures, we learned that decision trees are nothing more than simply separating data using if-then-else logic. The algorithm goes and explores every single possible variable, and then it tries many different ways of splitting the data. It finds the optimal split. When you're done, you can end up with a decision tree. This is an example right here. This is nothing more than a series of if-then-else rules. For example, if I don't know, this is a decision tree that will predict car damage. If I don't know anything about you, your average car damage will be $1,500. But if you live in the country, your damage will be much lower. If you live in the city, it will be higher. If you have a salaried job, you will have a lower damage. If you have a blue-collar job, it's a higher damage. So it's just if-then-else questions. The advantages of decision trees are their very fast training time. They handle outliers. They are really easy to interpret. They're simple to deploy. If I know nothing more than a series of if-then-else rules, I can put that into a computer program or an Excel spreadsheet or anything else really simple. And also, when I run these over and over again, I tend to get the same accuracy. So these are really, robust algorithms, and they're very popular. The problem with decision trees is that they have coarse segmentation. So that means everybody in a leaf gets the same prediction. Also, a small change in the input data can give me a very different output. So let's take a look at that real fast. So here's a decision tree, and let's look at what I mean by a coarse output. So what that means is that let's take a look at this particular leaf right here. And you can see everybody in this leaf has the same damage, $623. So the problem here is that it does not differentiate on anything. So for example, if I have a person whose travel time to work is 43 minutes, and I have a person who has a travel time to work of 1 minute, we can all agree that the person who's driving in his car for 43 minutes probably has more risk of damage than the guy who doesn't drive. Well, they're all in the same bucket. They all get the same, they will all get the same score. So it doesn't differentiate. It's not fine, it's coarse. So it's not very granulated. So what else is the problem? Well, the other problem is that decision trees are very sensitive to small changes in input. Let's look at this again. I have a person who, let's say it takes them 43 minutes to get to work. So that's 43 minutes. Their damage, if they crash their car, is probably going to be $623. Now, what happens if they move across the street and it now takes 1 minute more to get to work, 44 minutes? Well, if that's the case, then with 1 more minute, the person moves from here into here, and suddenly his risk or his damages go to $1,700, almost 3 times as large. So you can see that decision trees, although very useful, do have some drawbacks. With that in mind, we're going to try to correct these shortcomings with 2 different algorithms, the random forest and the gradient boosting. Now, before we do that, we first have to discuss a concept called an ensemble model. Well, what is an ensemble model? An ensemble model is a real simple idea. It's just you build a lot of models to do the same thing, and then you combine them. You take an average. It's based on a famous statistician named Galton, and he had a concept called the wisdom of the crowd, in which he found that when you take the guesses of a lot of people and average them, it tends to be a very good estimate of the truth. He found this when there was a contest on how to weigh cows, or what was the weight of a cow, and nobody could guess the weight of the cow, but when all of their predictions were averaged together, it was within 1 pound of the weight of the cow. So this is the same concept as being used for decision trees. So let's first take a look at random forests. So what is a random forest? A random forest is an ensemble model of decision trees. So what we're going to do is we're going to build a bunch of decision trees, and then we're going to average them together. Now, what do each of these trees look like? So if I have a forest of, let's say, 50 decision trees, and each decision tree is trying to predict something, let's say damages of a car or the probability of crashing your car, each tree tries to predict that. Now, the thing that makes these random forests is that each tree is random. Okay, well, what do I mean by random? Well, the size of the tree is going to stay the same. So if I said if I build one tree and I say I want it to be, let's say, 10 levels deep, if I build a random forest, I still want it to be a big tree. But what makes it random is I don't use all the variables. So if I have, let's say, 4 variables, A, B, C, D, I may not want to use all 4 variables. Tree number 1 might just use variable A and B. Tree number 2 might use B and C. Tree number 3 might use C and D. And the variables that the tree gets to use are randomly selected. They're not all the variables, just some of them. Also, I don't use all the data. So if I have 100 records, first tree, I might just randomly take 50 of those records and build the tree. Then I put them back in the box, shake it up, and for the next tree, I only use a different 50. So I'm going to use a small subset. Then when I'm done with getting, let's say, 50 or 100 trees, I'm going to average them together, and that's going to give me a good prediction of estimate of what I'm trying to do, crashing the car or damages, for example. So the advantage of the decision tree is that it's going to fix the problem of the decision tree having coarse answers, and also that the tree is very sensitive. The random forest is not coarse and it's not sensitive, so it fixes those problems. It also does all the things that the tree does. It can handle outliers, handles complex functions, consistently gives the same accuracy. It's a very robust algorithm. So why don't people use random forests all the time? Well, the reason why is that they are difficult to put into production. Decision tree, if then else rules. Random forest, I have 50 or 100 trees, so I got a lot of rules. It's not so easy to use. It's a black box, so I cannot interpret that. And also, in some places, like in the United States, it may not be legal to use a random forest for some reasons, for some models. For example, consumer credit or automobile insurance. I might not be able to use these in some places because you cannot interpret them. The government wants, I can use it for marketing or other things, but for credit, I can't use it for that because I cannot interpret. So now let's look at gradient boosting. It's very similar to random forest, but how is it different? Well, it's still an ensemble model of decision trees, but the difference is that gradient boosting is made up of small trees. The random forest is made up of big trees. So gradient boosting is little trees. And how are the trees trained? They're trained, first, they're very short. So that's how they're different from normal trees. Also, The random forest only uses some of the variables. The gradient boosting uses all of the variables. What about the data? Well, the gradient boosting uses all of the data, except that each time it builds a new tree, it adds records. Well, what records does it add? It adds records on the ones it got wrong. So it's always trying to fix the thing that it got wrong. So the number of records grows with the gradient boosting. And then when I'm done, I might have 50 little trees, and then I'm going to average them together, just like the random forest. Advantages, the same advantages of the random forest, you get the same advantages for the gradient boosting. Disadvantages, same thing. Difficult to deploy. It's a black box. I don't know what's going on. And it may not be legal in some cases, not all, but so you have to, before you use a random forest, especially when it comes to like lending money, because we have fair credit lending laws in the US. We have the Department of Insurance wants to make sure you're not discriminating against people. So before you use it, you got to check the laws. It's not always illegal. You got to look though. So let me explain, since gradient boosting is a little bit tricky, I'm going to explain it with a little example. Okay, so let's say I have this data right here, and I want to separate the plus signs. These are the plus signs here, and the minus signs. Well, if you recall, the gradient boosting only makes really very short, or like one split. It doesn't do a really short tree, one split. So let's say this decision tree, this gradient boosting says, okay, I'm going to try to split these as best I can with one line. And it says, draws it right there. Okay. So when it does that, everybody on the left side is going to be a plus, and everybody on the right side is a minus. So I got these two guys are right, and these 5 guys are right. Unfortunately, I didn't do so well over here. These guys are wrong. So because they are wrong, I'm going to have to do something about that data. So what I'm going to do is I am going to, you'll see that I'm going to make these guys smaller, or these guys that I got wrong are going to be more important. I'm going to make them bigger than everybody else to show you that they're more important. What I'm doing in real life is I'm just adding records to the data set. And then the guys I got right are going to get smaller. They're less important because I'm oversampling the guys I got wrong. So now I've got this guy right here. And now I'm going to build another model. Well, okay, how do I do that? Now remember, these big guys are more important. So the gradient boosting is going to try to get these guys. They're more important for him to get those guys right than the little guys. So now the gradient boosting says, well, okay, I got this guy here. And I'm going to say everybody on the right is a minus sign and everybody on the left is a plus sign. Well, that's good. But now I miss these guys. Well, now they get to get oversampled, and I'm going to add more of those guys to the data set. And so they become more important. So I'm showing that by them being bigger. These ones are still important. These guys aren't really very important because I keep getting them right. So they're not that important. Now the gradient boosting says I'm going to build one more model. And then because these guys are so important and these guys aren't so important, he draws the line right here. Now I got 3 decision trees. I'm going to combine these 3 decision trees by averaging them. So this was our first decision tree from early. And then later on in our demonstration, we had a tree that looked like this. And then finally, we had this guy. If I average these, I'm going to get a model that looks like this. So if I have, let's say, somebody in this range, so a little character right here, would it be a plus sign or a minus sign? Well, this guy thinks it's a plus sign. This guy thinks it's a plus sign. This guy thinks it's a plus sign. So that's a plus sign. What about over here in the corner? Well, he thinks it's a minus sign. He thinks it's a minus sign. He thinks it's a plus sign. It's a minus sign. They're voting on it. So you see that I got 3 models that aren't that good, but combined, they do a great job. That's the idea of a gradient boosting. Let's compare them. Well, why would you want to use a decision tree? They tend to be fast, easy to interpret, and they're easy to deploy. I mean, they're if-then-else rules. Random forests, because I got 50, 60 trees, they're going to be slower to create. Same with the gradient boosting. Can I interpret them? Not really. Are they difficult to put into production? Yes, they are. Not impossible, but difficult. So trees have a lot of good advantages, but the accuracy of the random forests and the gradient boosting are excellent. They do a great job. Trees are good, but these guys are better. And the output is more granulated. So if you recall, these guys had a course, everybody in the bucket has the same answer. You don't have that problem with these guys. What about if I change the input variable a little bit? It's just a small effect on these guys, but it could have a big effect here. Remember when I move across the street and my travel time to work went 1 minute, and suddenly it was it was a big change on my output. What about the number of trees? Well, if you recall, decision tree is just one tree, but I got many trees and many for the random forest and the gradient boosting. What about the size of the trees? Well, the decision tree is a full-size tree, and so is the random forest. The gradient boosting is just a little tree. What about the variables? Well, I use all the variables for the decision tree, and I use all the variables for the gradient boosting, but the random forest only uses some of the variables. What about the data? Random forest only uses some of the data. Decision tree uses all the data. Gradient boosting uses all the data, and then it starts adding to it. So he's got extra data. So these are the differences and the pros and the cons of the various algorithms here. And we're going to take a closer look in some later videos.